The list of people here is actually incomplete. It includes people who have been with the group for 20 years. It includes our postdocs, researchers, students, including undergraduates. But I haven't mentioned people who are doing work in the X-rays and radio and far infrared that we can't do at Keck Observatory because I didn't want to completely fill this slide. A lot of people were involved in this research. So let me start by setting the stage, tell you a little bit about what we're dealing with when we talk about the center of our galaxy. We live in a very quiet, uneventful part of the galaxy compared to the galactic center, and really that's the way we want it, because the galactic center, as active as it is a fairly hostile place, with supernovae going off frequently, with a high background of X-rays and gamma rays and cosmic rays, and with all that's going on, we probably couldn't expect to last very long if we were to visit it. But imagine that you could visit it. Transport yourself to the center of the galaxy. For every star that we could see, if you walked outside and looked at the nighttime sky here in Hawaii, at the galactic center, you would see 1 million stars. So what I'm saying is our naked eyes here on Earth can see several thousand stars at a time on a good site, like the top of Mauna Kea. But if we were standing on an Earth orbiting a star at the galactic center, that several thousand would translate into several billion. So the density of stars at the galactic center is so high that we encounter a whole new raft of possibilities for what stars can do and what kinds of stars we might find. Some of those stars are extremely bright, so bright that if we were, again, standing on that planet at the galactic center, several of the stars would be as bright as the full moon, if not brighter. It depends on just where you stand and how far away you are from those stars. So it would be a really bizarre sky. I'm sure you would have no trouble seeing your way around in the middle of the night from a planetary surface at the galactic center. So the galactic center should be really easy to study, right, with all those bright stars and such a large number of them. The problem is that there's a lot of dust in our galaxy, and only one visible photon in a trillion can reach us from the galactic center. In the era before infrared astronomy came to the fore, people didn't even know where the center of our Milky Way Galaxy was because they couldn't see it with visible light and classical astronomy. We had to go into the infrared to see it. In the infrared, we can do much better. And the reason, of course, that light doesn't reach us is because the galaxy, our Milky Way Galaxy, is such a dusty place. And light can't penetrate that dust. But in the infrared, it can. And that's the solution. In the infrared, the wavelengths we use at the Keck Observatory, we can see 10% of the light that's emitted. And that's enough. We can do good astronomy with 10% of the light that gets emitted. The rest of it gets absorbed by the dust, but 10% is enough. And the other factor in our favor here is that the Keck telescopes are exceptionally well equipped for infrared observing. There are several powerful instruments, world-leading instruments at the Keck Observatory, which permit us to do things that you just can't do elsewhere. If we take a distant look at the galactic center in the infrared, this is what we see. This is from the 2-mass all-sky infrared survey that shows what the center of the galaxy looks like in the infrared. It's a big region. This is 400 light years from top to bottom. So we're looking at a huge portion of the center of our galaxy. But keep in mind that classical astronomy couldn't see this glow at the center of our galaxy because the visible light just wasn't coming through. And even this infrared light is just barely getting through. As you can see, this central cluster of stars, what we're seeing here is the red giants that dominate the light output of the center of the galaxy. And you see lots of dust patches that are so thick and so dense that even infrared light can't penetrate those. And you can also imagine that we're quite fortunate that one of these patches isn't sitting right over the central part of our galaxy. I wouldn't be here talking to you today if one of these dust patches were sitting right here. One almost is. This black region here is a dusty patch that just misses the galactic center. So we can study these stars pretty well, and here's a greater detail of that central region. But these are images made with classical telescopes that don't use the technologies that we now have available to us. And so all the stars that you see here are all piled up on top of each other with the literally hundreds of millions of stars that are in this image. Seeing the individual stars and studying them is a real task, because the stars are all blended together. So we turn to the technologies that were developed here at the Keck Observatory, and for which the Keck Observatory is a world leader, adaptive optics, to get the crisp images we need to resolve the individual stars. And the technology of adaptive optics corrects for the blurring effects of the Earth's turbulent atmosphere. Basically, what is done, and I'm boiling this down to really crude, simple terms here, is recognize that the Earth's turbulent atmosphere deforms the wave fronts of light that come through the atmosphere from the stars that we may be trying to observe, and that blurs the light enough that we can't separate the stars one from another. And so the wave fronts have this distorted shape. And if we just reflect those wave fronts off of a flat mirror, then the light that comes into our instruments is also aberrated or deformed, and thus we get the blurry images. But if we can apply adaptive optics, which means putting this deformable mirror in the light path, and in real time, at a rate of hundreds of times per second, deform that mirror in exactly the right way needed to correct for the distortions that are introduced by the Earth's atmosphere. Then we can get a corrected wavefront that is what we call plane parallel, and that gives us the opportunity to see the individual stars very clearly. Before I show you how that correction looks, you might be wondering, well, how do we know how to correct the mirror? The answer is that we probe the atmosphere. One way to do it is to find a nearby star and monitor what the atmosphere does to that star. And if you're lucky, there is a nearby star that's bright enough to do that. And we call that kind of star a natural guide star that can be used to probe the atmosphere and make the necessary corrections. But most directions in the sky don't happen to handily have a nearby star that we can do that with. So we use a laser. And the laser makes an artificial star at the top of the atmosphere. We tune the laser to a spectral line of sodium, and at the top of the atmosphere happens to have, about 85 kilometers up, a thin layer of sodium atoms that result from the disintegration of micrometeorites as they enter the atmosphere. And so as the laser hits that thin layer of sodium atoms that's turned into gas and is residing there temporarily, it glows, and we can see a natural, an induced guide star. We make our own guide star with the laser. So this is the laser propagating out from the side of one of the Keck telescope mirrors, and it's an orange light, and that is the wavelength that we choose because that's where sodium has its resonant frequency. You can't see the guide star here because it is in fact 85 kilometers away, but you can see where this is pointing, and we pointed exactly where we want the telescope to be able to focus. Actually, this slide is already fast becoming out of date because the even newer technology has the laser being launched from the center of the telescope, right from this apparatus here, the prime focus unit. And so the side launch lasers are soon to be a thing of the past for both of the two Keck telescopes. Well, This image is the kind of image we get if we don't have adaptive optics to correct the blurring of the Earth's atmosphere, with adaptive optics turned off. But if we turn adaptive optics on, the blurring reduces dramatically. And where we could only see a few stars in this central arc second of the galaxy before, we can now see on the order of 100 stars, or possibly even more if we really make an effort. Here you don't see them all, but what started off as this vague blur where you could see maybe 3 or 4 stars has turned into hundreds of stars. So we use the lasers, and sometimes we use lasers on both telescopes at once. This image was taken at a time in the last couple of years when and we've done this a few times, when we've used both telescopes equipped with adaptive optics to study the center of the galaxy. And you can see from where these lasers are pointing where the center of our Milky Way Galaxy is. It's in the constellation of Sagittarius. And these lasers end up pointing at a dark spot. That's because this image, this photograph, was made with visible light. And as I told you, no visible light gets through because of the dust. So all we see here in the visible light is the dust that's along our line of sight between us and the center of the galaxy. Peeking out above and below that layer of dust are the great star clouds of Sagittarius, where the light from the stars isn't blocked so much, and you can see the spectacular glow from the light. If there was no dust in our galaxy, the center of our galaxy would be extremely bright. It would be awesome to behold. Already the Milky Way from Hawaii is awesome to somebody like me from Los Angeles. But without the dust in our galaxy, it would be hundreds of times brighter. So we turn to the infrared, where now we can peer through this veil of dust. And if we look at an image made, now this image didn't use adaptive optics, but this shows this image is to show the colors of stars in the infrared. Now these are false colors, because infrared light doesn't have the kind of colors that our eyes are adapted to. So we translate infrared wavelengths over to the optical part of the spectrum so that the colors make sense to us. So this blue star here, for example, in the visible part of the spectrum might be red. But when we translate into the infrared, it has more energy going out at the shortest infrared wavelengths, so we call that blue, just as we would for a star that emits more light at the shortest visible wavelengths. All these blue stars that you see in this image are not at the galactic center. They're in the foreground, along our line of sight. After all, we live in a galaxy with 100 billion stars. You might expect that some of them have to lie along our line of sight between us and the center of the galaxy. And those stars that show up as blue aren't behind so much dust, so they aren't reddened by the dust. But you can see that a lot of the other stars here in this image are reddened by the dust, because the dust not only blocks the light, but it makes it redder. For the same reason that sunsets are red, a lot of the blue light gets preferentially scattered before the red light does. So in this region here, right around the center of the galaxy, and the dynamical center of the galaxy is right there, is where you have a lot of dust that reddens the stars. But some of these stars are red simply because they're red giants. The yellow-orange stars, if they're not reddened because of dust, are the red giants. I'll come back to talking about this one spectacular red giant here, this yellowish star. The white stars that you can see here are the hot, young, massive stars, and I'll talk about those as well, because they really are remarkable in many respects. So we can use colors to start the process of determining what kinds of stars we're looking at. But even more useful than colors is to take spectra. And again, the Keck telescope is equipped with some powerful spectrographs. We use the OSIRIS integral field spectrograph to take spectra like this in the infrared. And we can distinguish between young and old stars because of what spectral lines are present. For example, young stars show this hydrogen line called bracket gamma. Old stars have sodium lines in them. Now, this is coincidental that it's sodium. Sodium appears here as well, just because it's in the atmospheres of these red giant old stars. And we can use that to distinguish the young and the old stars. So let me start by talking about young stars. When we look at the center of the galaxy, and this is a 3-color infrared image of the center of the galaxy, we, again, are translating the infrared colors over to the visible so that our eyes can appreciate what we're looking at. We see red stars and white stars, and some are even blue. A bluish star up here that's probably a foreground star because it's not extinguished so much by dust. When you see really red objects like this and that, what you're looking at is dust. In addition to stars, this region has a lot of streams of gas and dust that are falling toward the central black hole, which is called Sagittarius A star and located right where that arrow is pointing. So now we're looking right smack dab toward the center of our galaxy. And what we see here is a host of very bright stars. These are the stars that would be brighter than the full moon if you were standing on a planet in this region. Now, what we've done with the spectroscopy and using the colors is to determine which of these stars are old and which are young. And the X's here mark all of the young stars. I'll go back and forth, and you can see that there's a lot of young stars here. And that's a surprise. Young stars weren't supposed to be there. And the reason for that, at least if you asked somebody 20 years ago, he or she would have said, well, you can't have young stars there because there's a supermassive black hole that exerts such powerful tidal forces that stars couldn't form. If you get a cloud of gas that tries to collapse under its own gravity, the tidal forces of the black hole would pull it apart, and it couldn't collapse to form stars. In fact, in the early 90s, people saw young stars there, and they said, well, there can't be a black hole there because there's young stars. Now we know better because the work we've done at UCLA and work done elsewhere has demonstrated very clearly that there is a supermassive black hole that's 4 million times as massive as our sun, sitting right there at the center of the galaxy. So we have this paradox, the paradox of youth. What are those young stars doing there? They're there. They are there, and we now understand that they must have formed under very unusual conditions out of a massive rotating disk of gas that was present at the center of the galaxy about 4 or 5 million years ago. These stars all formed in one fell swoop, in one massive event 4 or 5 million years ago. And it must have been really cataclysmic when that happened, because star formation is a violent process. A lot of energy gets released, but at the same time, all that gas in the presence of the central black hole would also release a lot of energy as some of the gas would fall into the black hole and get extremely hot on the way in and radiate across the electromagnetic spectrum, powerful amounts of electromagnetic radiation. If we could live in an era where our central black hole is radiating, as it must have 4 or 5 million years ago, the galactic center would be a very powerful light source. Now, we can see this disk, and this is one of the reasons we know that the stars must have formed out of a disk. We can see that in the motions of the young stars, and that's one of the things we've been doing, is year after year, we go back to the Keck telescopes and take images and follow these young stars as they orbit the central black hole. And we draw here on negative images of the star field around the central black hole. We draw the arrows that represent the directions of motion on the sky of the stars that we're following. And we divided the stars up into 2 groups, the red group and the blue group. It's like the states during an election. The red arrows are all kind of conforming to each other. I don't know what party that corresponds to. But they all go around the galactic center in the same direction. And when we use what we know about their velocities, we can infer theoretically that they're all more or less in a disk of stars that are all orbiting in the same direction. The blue stars are moving randomly. Now this is a zoomed in version. If we zoom out, we get more stars. All of these are young stars, mind you. I'll talk later about the old stars. And we see a lot of stars in the disk and a lot of stars moving randomly. Here's an animation of the orbits of stars as we have measured them. And of course, this is idealized and put together by the National Center for Supercomputing Applications in Illinois using our data. And so these are real data for the stars that we're following. The orange stars are the old stars. The greenish stars are the young stars. And the purple stars are stars we haven't figured out yet, so we don't know which to assign them to, young or old. But you can see this disk of stars, if you zoom out far enough, that there's a conformity to the motions of stars in this disk. We haven't put all the stars on this disk because it would get too messy and look like a haystack. But these are most of the stars whose orbits we can follow. And look at the center here. There's two kinds of dynamics going on. There's the disk of stars out here, and at the center, where the stars are moving fastest, are the stars that are moving isotropically, that is, in all directions. Let me see if I can just go back and restart that a bit. Yeah. I want you to notice that the stars at the center of this configuration are closest to the black hole, and like the planets of our solar system, they move the fastest. The planets closest to the sun whiz around the sun much faster than the planets that are furthest from the sun, and the same laws that Kepler and Newton derived in the centuries ago apply to the stars that orbit the black hole. Now, how do you form stars in a disk? There's a lot of ideas out there, but this remains unknown territory. I'll just show you one model just because it gives you an idea of the kinds of imagination that people have here. This will replay a few times. What's happening here is that a cloud of gas is falling straight toward the central black hole, and the central black hole is over here, and you can see that everything orbits around it when it gets there. And as that cloud of gas reaches the black hole, it gets compressed. It gets compressed enough that parcels of gas can collapse under their own gravity to form stars. And these little white dots are the stars that are formed in this model. There are problems with this model, so I'm showing this just as an example of the kinds of creative ideas that are out there, but the number of models that people have come up with for how you get stars to form around a black hole in a disk are multitudinous, and I don't have time to talk about all of them. Now, massive stars that are so bright that we can see them from our distant perspective of 25,000 light years are burning their candles at both ends. They live fast and they die fast. And they die in the end as supernovae because they're very massive stars. And the age of this cluster, the central cluster of young stars, 4 or 5 million years, that may sound old, but that's really a drop in the bucket of cosmic time. For 4 million years, that's 1/1000th the age of the sun and the earth. And these stars are already reaching the end of their lives, and some of them are now exploding as supernovae. And supernovae leave behind stellar remnants, black holes, and now I'm talking about little black holes, stellar mass black holes, not supermassive black holes, and neutron stars. Depending on what the mass is of the star that has become a supernova, it leaves behind one of these possible remnants. Now, if if these massive stars create a black hole or a neutron star, the neutron star or black hole has no place to go. At the center of the galaxy, you're at the bottom of the well. The gravity of our galaxy is trying to pull everything toward the center of the galaxy, and in order for a star to climb out of this deep gravitational well at the center of our galaxy, you would have to have a really high speed, and these stars don't have that. So they're trapped there. And as these young stars form, and they probably form over and over again throughout the history of the galaxy, their remnants pile up. So we must imagine that our galactic center has a cluster of neutron stars and black holes that's permanently there, and it's an invisible cluster. These stellar remnants orbit the central black hole, and once in a while they may actually dive into the central black hole. We haven't seen that happen. But we also haven't seen these remnants because these are such small objects. If you take a neutron star and placed it on the Kona coast, it wouldn't even stretch from Kona to Kauai. They're only about 10 kilometers in size, these neutron stars. Of course, if you placed a neutron star on the Kona coast, it would suck up the Earth in a microsecond. But that's because a neutron star weighs more than the sun, and that's 1 million times more massive than the Earth, and yeah, we wouldn't want to do that. But these remnants must be there because there's no place to sweep them under the rug. These massive stars are living and dying at the galactic center, and their remnants have to be left behind. Well, is there any evidence for these remnants? Excuse me. There is some evidence. X-ray astronomers have seen transient X-ray events. Here is a sequence of X-ray pictures of the galactic center made with the Chandra X-ray Observatory that's now orbiting the Earth and still taking data after 15 years in operation, and it's still chugging away. The central black hole, Sagittarius A star, is itself a bright X-ray source because some of the gas that's falling into it is emitting X-rays as it falls in. So it's a kind of permanent feature there. But these circles surround places where transient events have occurred from time to time. Big X-ray flashes that last a few months and then die out. And what these probably are binary systems where a normal star is orbiting a black hole. And the normal star and the black hole are happy to orbit each other, but the black hole gathers some material, some mass from the normal star into a disk around it, and that disk undergoes dramatic instabilities episodically and undergoes these X-ray flare events. So that's what we're seeing here. And so there is evidence that in this region, there are some black holes. It's hard to take a census of these, and it'll take us a long time, a lot longer than we have. Chandra won't be, the X-ray Observatory won't be up there long enough to really scope this out, but there is some evidence that those are there. Now I'll come back to black holes in a bit. Let me go to that central part of the cluster of stars that I showed you in that animation, the stars that are orbiting in all directions. Here's a blow-up of the orbits that we determine using the Keck Observatory data that we gather in the infrared. We can follow these nice orbits, and for the most part, these orbits are just exactly the kind of orbits that Johannes Kepler described when he was describing the orbits of the planets around the sun. They're elliptical orbits, and some of them don't look so elliptical because they're at an angle to our line of sight. But we can fit all these orbits very nicely using 300-year-old physics. And one of the goals of our Galactic Center group at UCLA is to bring our physics into at least the 20th century by testing Einstein's theory of general relativity using the orbits of some of these stars. When you have such a large mass at the center of the galaxy, the stars that are orbiting it have to move fast. This star, for example, which is kind of has an edge-on orbit, as it swung around the black hole in about 10 years ago, it was moving at 12,000 kilometers per second as it came close to about 90 astronomical units, about 90 times the distance between the Earth and the Sun from the black hole. And, well, 12,000 kilometers per second is 4% the speed of light. So an entire massive young star moving at 4% the speed of light gives you an idea of the dynamics of this whole region. All of these stars are moving rapidly. That's just the most extreme case we've seen so far. So this cluster of stars is what we call the S-star cluster. And let's start this animation. Yeah. The S-star cluster are young stars. They're close to the black hole. They have very high speeds, as I said. And their orbits are randomly oriented, very elongated in general. And so, as I said, these are the stars we're going to use to probe our general relativity in coming years. Well, the real question is, how did the S-stars get there? This animation shows an idealized version of the orbits that we've determined. And this star here, for example, has a period of 15 and a half years as it orbits the center. It happens to be the brightest one that we're following. And it will swing by the black hole in 2018. And so we're going to be poised and ready to observe that as carefully as we can in 2018, because that's the star that we're going to use to do the primary test of relativity. Well, so the question, how do the S-stars get there? They can't form there. They're too close to the black hole. And as I said, the black hole will prevent star formation that close to it. So there's a way to do it. And this is the most widely accepted hypothesis for how the S-stars got there. You start with a binary system at some distance away. So these two stars are orbiting around each other, and the ensemble of these two stars itself is going to orbit by the black hole. And if nothing were to happen to this binary pair of stars, this is the trajectory that the pair would follow. But as it swings by the black hole, the tidal force of the black hole, the difference in gravity on this star and on that star, pulls the binary apart and traps this star. And this star becomes one of the S-stars. It goes into an elongated orbit around the black hole. The other star gets flung out at tremendous speeds. It's what we call a hypervelocity star. And those we've seen. We don't see them in the galactic center because they don't stay around long enough. We haven't actually seen this process occur, but we can look out in the halo of our Milky Way Galaxy and find stars that are moving out of our galaxy at high speeds well in excess of the escape velocity from our galaxy, and they're moving away from the center of the galaxy. And so this is just what you would expect from this kind of interaction. So the evidence is all in place, I think, that supports this kind of model for how those S-stars got there. So these are good examples of extreme stars. The hypervelocity stars are the extreme velocity stars. The S-stars are the extremely close to the black hole stars that have no business being there, except that this special dynamical event allowed them to be there. So far, I've just talked about the central cluster of our galaxy, right in the central few light years. But there are other clusters, other massive young clusters in the galactic center, with the names the Arches cluster and the Quintuplet cluster. And we've been studying those as well with the Keck Observatories. These just happen to be Hubble Space Telescope pictures, because the field of view of the Keck telescopes is small compared to the size of these clusters. So to get the big picture, I've used a big Hubble picture. But these clusters, too, are some of the most massive clusters in our galaxy. In fact, the Arches cluster shown here has about 10,000 stars, like the cluster in the central part of the galaxy. It's even younger. It's only 2.5 million years. So this cluster is a real baby. It just formed. And none of its stars have finished their lives yet. 2.5 million years isn't quite enough. Maybe a million years from now, these will start popping off as supernovae. There's hundreds of massive stars here, in fact. And so the stars that you're seeing here are the most massive luminous stars. The density of stars here is incredibly high, and there are other impressive clusters in our galaxy, but none that quite reach the high densities and the high masses of the Arches cluster. This cluster, like the cluster in the central few light years of our galaxy, probably formed all at once. You can't just form one star at a time out of a cloud of gas, because if you form one star, it'll blow away the rest of the gas. So you have to form 10,000 stars all at once. So the formation of these stars 2.5 million years ago, about 100 light years from the center of the galaxy, was an impressive event. A lot of these stars we're finding with the Keck telescopes, have disks of gas and dust that are forming planets. When you're that young, only 2.5 million years, the disk of gas and dust out of which the star itself formed is still present. And the dust is in the process of forming planets. Now, we can't see the planets at the distance of the galactic center, but we have been able to find infrared emission from all that dust around some of these stars. And these circles are just identifying where the disks are present. Now, as an aside here, let me show you an image from the SOFIA Airborne Observatory, the Stratospheric Observatory for Infrared Astronomy, which often comes to Hawaii to make a stop. This image is in the far infrared, so much longer wavelengths than what we observe with the Keck telescopes. And it's of the quintuplet cluster, which is located here. But what this is showing is some really extreme stars located here and here. These stars are what are called luminous blue variables. They're the most massive stars. This star, some people have claimed, has a mass 200 times the mass of our sun. That may or may not be that massive, but it's certainly on the order of 100 times as massive as our sun. Stars that massive are unstable. You can't make a star like that and expect it to hold itself together, because it's so luminous that even the light coming out of the star is pushing off the outer layers of the atmosphere. And that's what you see here. In the far infrared with the Airborne Observatory, you can see the dust that forms in this powerful winds coming off of a star like this. The wind coming off of a star like this is really powerful. It's the mass of the Earth every 4 hours is being blown out of a star like that. Here's another one that's even more symmetrical. This one's a little bit skewed because the bubble that's being blown by that wind is being impacted by winds from the other stars in that cluster. Okay, now let me turn now to old stars. I'm going to start by talking about the brightest star in the region, the red supergiant, IRS-7, which is this bright star right here. This is a negative image. Sometimes we like to look at negatives because we get tired of looking at bright stars on a dark background, and so we'll do the reverse. Here's where the black hole is, and here's the IRS-7, the red supergiant. This is a star that's so large that if it were placed at the location of the sun, we would be inside it. It's a star that has a strong stellar wind, and you can see that wind in the radio, and this is what I'm showing you. Superimposed on that is contours of radio emission. observed with a very large array in New Mexico. It has a cometary tail because its wind, the wind from that star is hitting a wind that's coming from down in this region. All those bright young stars, and maybe the black hole as well, are blowing a powerful wind that's impacting this supergiant star and blowing back in a bow shock the wind and dust coming off of this star. So that is an extreme star. You don't find a star that looks like a comet anywhere else but the center of the galaxy. Now, do stars run into each other if they're so densely packed? Yeah, they do. And not very often. Here's a simulation of a stellar collision. Of a stellar collision that was made by Joshua Barnes, who's at the Institute for Astronomy in Oahu. He has modeled these stars as groups of particles and shown that under some conditions, like this one, when the stars collide, they coalesce. Of course, they make a real mess. They blast each other apart, and then over time, gravity pulls them back together again. That's probably not what's happening at the galactic center. At the galactic center, more likely, the collisions are more like this. The stars are moving rapidly, and they graze each other, and they kick off a lot of the atmospheres of each other as they go, but they move on their merry ways and don't merge. That's the kind of collision that takes place between normal stars once in a while in the galactic center. We haven't seen that happen yet. But what happens at the end of a lifetime of a normal star? It becomes a red giant. And when you're a red giant, you're a sitting target. You're big and you're doomed in the galactic center. It's a destruction derby for red giants. We've found, using the Keck telescopes, that red giants are missing in action at the galactic center, and that's no surprise, really. There's several possible reasons for that, but one is that they are simply annihilated by collisions with stars, black holes, neutron stars, all of which could be present there. Now, theoretically, these old stars that form red giants should be strongly concentrated around the central black hole. But instead, we see that maybe there's even a dip in the concentration of the old stars. And that tells us that there's a good chance that a lot of these red giants are being destroyed. Here's two frames of an interaction between a black hole. There's this tiny black dot here, which is the black hole, very small compared to the red giant. The black hole itself is 10 times the mass of the sun, but the star itself may be only the mass of the sun. So the black hole has much more gravity, and as it enters the atmosphere of the star, it wreaks havoc. And here's the aftermath. Here's the black hole. Now it's accreted some of the atmosphere from the red giant, and here's the core of the red giant is exposed. A lot of this gas from the atmosphere of the red giant is just being splashed to the far corners of the galaxy. So these kinds of collisions, whether it be with a black hole, a neutron star, or other stars, are probably occurring there. So this is the destruction derby aspect. Now, have we seen this happen yet? No, but when it does happen, it'll probably be pretty spectacular. Once in a while, a star, be it a black hole or a normal main sequence star like the sun, will encounter the supermassive black hole. It's calculated that that'll happen about once every 20,000 years. And when that happens, all hell breaks loose. The amount of energy that will release is about 10 times the energy of a supernova, as half the star gets swallowed by the black hole, and the other half of the star gets sprayed out to the rest of the galaxy. All right, now I'm going to talk about neutron stars for a few minutes. We can't see them with the Keck Observatory, at least not at the galactic center. I think some neutron stars that are nearby us in the galaxy can be seen. But there are some neutron stars present. Here is a radiograph of the center of the galaxy. The black hole is located right here, and it's a strong radio source, but I've saturated that part of the image in order to show you this supernova remnant. This is the blast wave of a supernova that occurred 9,000 years ago and is blowing a big bubble. In fact, it's really interesting because this bubble is passing over recently, has passed over the center of the galaxy. And that cluster of young stars that I talked about earlier is inside this bubble. And this blast wave is still propagating out. But what does this supernova leave behind? Either a black hole or a neutron star. Well, we found the neutron star, and there it is. We call it the cannonball because it's careening away from where it was created. And this is commonly believed to happen. When you create a neutron star by collapsing the core of a massive star, it doesn't just sit there. It gets a kick. And this is moving at 500 kilometers per second. Here's a blow up with higher spatial resolution. It has a little tail pointing back to where it was created. That's one neutron star that we know is present there, and clearly neutron stars are created there. It's a bit surprising that we don't see more supernovae given the abundance of young stars there, that we don't see more supernova remnants like this. Now, another neutron star, this makes a good story because it happened just in April 2013, almost 2 years ago. What we're looking at here are X-ray images of the central black hole. This is Sagittarius A star. It's a constant source of X-ray emission. And this is the way it was for many years between 2005 and 2008. It hasn't changed much. But in April 2013, a powerful blast took place nearby. Now, in this image, also an X-ray image made with the Chandra X-ray Observatory, you don't even see the black hole anymore because this is so bright that the contrast isn't large enough to even see this constant emission from the central black hole. What this is, this object with this particular phone number, is a magnetar. A magnetar is a young, highly magnetized neutron star. It has to be young. This neutron star had to have been created relatively recently. Again, only 10,000 years or so ago. And in the realm of cosmic time, that was like yesterday. And so very near, only 2.4 arc seconds away from the central black hole, we have this evidence for a neutron star. And what's interesting about this is that for some time, everybody thought that this powerful explosion took place at the black hole. And it took weeks for people to really figure out that, no, this wasn't the black hole. This was something altogether new. And in fact, radio astronomers turned their telescopes on this object and saw they could see it moving. They could see its motion on the plane of the sky, and they saw, this is moving just like the stars in that disk. Here's the arrows representing the motions of the stars in the stellar disk, and here's that arrow representing that magnetar. Yes, this is a remnant of a star that was once in that disk. And so just in the last 10,000 years, there was an explosion there. But this left behind some mysteries. We only see that, well, one of the mysteries is where are all the other neutron stars that should be detectable there? This particular neutron star is a pulsar seen in the radio. All neutron stars should be pulsars for the first few million years of their existence, but none have been found. This one, we're finally seeing a pulsar at the galactic center. Where are all the others? And so it's a mystery I don't have an answer to. The other mystery is, where's the explosion? If this magnetar was created only 10,000 years ago, we should see a big blast wave bubble like I showed you before. Where is it? And so we throw up our hands. We don't know. Let me close out by talking about another mystery, the object we call G2. This is an extremely red object that we've been studying with the Keck Observatory. It's too red to be in a normal star, and it was discovered by Stephen Gillison and his collaborators in Germany, and the title of their discovery paper was "A Gas Cloud on Its Way Toward the Supermassive Black Hole in the Galactic Center." And they deduced that this was a little cloud of gas, only 3 times the mass of the Earth, which is nothing. It's a tiny fragment of gas. Here in this 2-color infrared image, it's located right here. Here's the black hole, and it's on its way to the black hole. In fact, schematically, here's what we know was happening, that it's following a nice orbit around the black hole, and as it approaches the black hole, it's getting stretched by the tidal forces of the black hole. And so this is just a schematic of it. Let me show you, in fact, an animation that was made by Chris Fragile of what they expect a 3 Earth mass cloud would do as it orbited around the black hole. It's going to have a hard time holding itself together. It doesn't have enough gravity, and it just gets sprayed, and a lot of it gets dumped onto the black hole. So as a result of that expectation, we all thought that when this G2 object comes close to the black hole, and it reached its closest point, by the way, almost a year ago, that a lot of gas would be dumped on the black hole, and the black hole would flare up. Well, that hasn't happened. We have been studying this, and we at UCLA have had a different idea of what G2 is. We think it's a star, a very unusual star, an extreme star. And this shows some of our observations from just last year, where we have all the stars, the S stars that are in the central arc second of our galaxy, all shown here. In this image, G2, as it's going around the black hole, is right on top of it. We can't distinguish it and resolve it. But the other stars, we know their orbits very well. We know where they are. Here's SO8, SO2, and the black hole itself. We can subtract all those out. And when we subtract them all out, there it is. There is G2. And this is after it supposedly passed through its close passage by the black hole. So it stayed intact. And if it were to stay intact, it had to be a star. So what is it? It's this very red object. Well, I don't claim that we have the final answer, but we find that G2 must be a star that's completely surrounded by an opaque halo of dust. And the way to get that I think we prefer, is that it's a result of the merger of 2 stars. As I've already shown you, stars can merge in this region. And the black hole can help out that process. When you have a binary star in the presence of the black hole can cause the orbit of that binary star to evolve over time until the 2 stars finally merge together. And when they merge, as you saw in that animation, all hell breaks loose, and the star gets really puffed up. And when a star gets that puffed up, its outer layers are cold and dusty, and that's pretty much what we see when we look at G2. We'll be following that. So the last mystery I'll leave you with is, why hasn't the passage of G2 caused any spectacular fireworks by the black hole? This big distended star should have dumped some gas on the black hole. Well, maybe it's doing that, but it just hasn't happened yet. We expect still, perhaps, that the black hole will flare up in the coming years, but it hasn't yet. Maybe that's yet to come. We'll be watching, and we'll be using the Keck telescopes. Thank you.